Hello and welcome to Pint of Science 2021. I hope you've enjoyed the other talks from other experts, especially my friends from Imperial College London. Tonight, we'll be discussing the future of AI, learning from others, with a panel of AI experts. I'm your host, Kate Highnam, and I have with me on the stream Isak Falk, a machine learning researcher from UCL, calling in from Italy, and Janith Petangoda, a machine learning researcher from Imperial College London, with me calling in from East London. A quick bit about myself. I'm a PhD student in the Electrical and Electronic Engineering department at Imperial College London. My research is in the intersection of machine learning and cybersecurity, specifically domain adaptation for intrusion detection. I'm also affiliated with the Alan Turing Institute in London as an Engage at Turing student. To preface tonight, this panel discussion is meant to be a super high-level conversation about the state of artificial intelligence, specifically in machine learning. It's intended for an audience members who have maybe read a few articles in the news on artificial intelligence and are curious about the progress in the field. For those of you with a bit more experience, I've included key terms to some relevant advanced topics, which I hope will motivate your interest in the field further. While we cannot discuss everything in the field, I believe that the theme learning from others best describes recent innovations, and hopefully by the end of the show, you'll understand why. We'll start the show with a brief background on how machines learn. This will set us up for a deeper dive into our guests' areas of expertise. Isak will go first, talking about learning to learn, followed by Janith discussing learning to transfer. After we hear from each expert, we'll open the floor to questions and our comments, so please enter your questions below or add us at the tags that you see on screen. So, without further ado, let's go ahead and get started. First thing to clarify for tonight are some terms that we might be using intermittently. For example, the difference between artificial intelligence and machine learning, and deep learning if you've heard of that. While all systems that seem intelligent fall under artificial intelligence, machine learning is a particular subfield within it. Machine learning, or ML as we might say tonight, covers those which use statistical methods and experience to perform tasks, which we'll go into more detail on in just a second. You might also hear us mention deep learning tonight, which is a particular subfield in machine learning. It specifically means methods using a particular kind of model called a neural network in various ways. But we won't go into this in too much detail, I think. Another note is the common reference to a machine that can learn. This is a colloquial term, or humor for the evening. But please know that when we say machine, we mean model or statistical model or program. They take in some input and give some output. Sometimes a model is within some kind of physical system or program to perform a certain task. And an easy way to think of this is as some robot, like this one seen on the screen, that behaves like a small child learning to interact with the world. Sometimes we have interpreted these instructions for the robot, and it might lead to different kinds of performance. But as we say, we're trying to teach it. So how do these machines learn? To understand this, we need to specify a few things. First, what kind of model are we training? Here, I've simplified it to a few colors: blue, or teal as it might look to you, or orange, white, brown, yellow, or is that green? And for those familiar with some models, the selection would be more like something like this. Maybe you're choosing from a Gaussian process, decision tree, linear regression, SVM, neural network, and of course, many, many, many more. And in deep learning, this choice or selection might be choosing its architecture. Under the hood, and continuing with this car analogy, you can think of them as a set of gears and knobs that we get to turn, fit, tune, which are represented by numbers and functions, also called parameters. Each kind of model has a unique format of how gears link together, and learning is just tweaking these parameters, turning, adjusting them, and we choose the parameters based on two things. First are the inputs. These could be pictures, text, spreadsheets, etc. Things will be given, things that we'll need to do something with. And from them, tune the parameters. But this is not just based on the input data alone. It's also based on the output. Analyzing its own output also guides how the parameters will be tuned. How this is done is largely dependent on the task that the model is trying to solve. Is it trying to classify the inputs? Is it a cat or a dog? Is it trying to score the inputs between a 0 and a 1? Give it a percentage or something? Or is it trying to just predict the next value in an input sequence? Sometimes when we're training a model, the ground truth is available. And if the ground truth is given to the model, which is like having an answer sheet to a test, then it can check its own answers. The parameters can be updated on questions it had gotten wrong, and it can reinforce which ones it got right. So hopefully it does better next time. Continuing with the supervised example, the teaching process looks a bit like this. Imagine I have a model that is trying to learn the difference between night and day. I give it some examples of inputs and corresponding outputs, also known as data and its labels. It then begins to reassess different gears and knobs to learn from the examples given. Some turn yellow, maybe orange, maybe they turn a few notches. Some of them you'll keep teal. So after it's been trained for a bit, we can give it new, slightly off-colored examples, and it can decide what its outputs should be without supervision. Hopefully it does a good job after we've trained it. Now, this looks like the model has done its job, and we can follow the same process to achieve artificial general intelligence, or AGI, but we're not quite there yet. And I hope that we can demystify maybe some of these thoughts we've had before. Since how it learns is just one portion of the challenges machine learning needs to overcome. Here I've generalized the main challenges considered when analyzing model development and performance. And yes, some of those definitely overlap. The first two result from what we just covered. Do we choose the right model? Is there a better one? Do we provide a good distribution of inputs and outputs? Were these similar to the new data we gave it when we stopped training it? Then there are other challenges. What if you had limited capacity or memory on the computer it's running on? Is the computing power limited? Is there a GPU or a TPU? Or maybe I'm too poor to have one. Is time limited in some way? For example, when your boss tells you that you have to have results by your next meeting. This could mean for training time or for time to run the model. And finally, is the model able to do what you want it to? This overlaps with choosing the best model, but we just covered a relatively simple task of distinguishing night from day. So how do we go from this to behaving like a human? We still don't know. So in this sense, models are limited in terms of their abilities to complete any task. So how do we solve more complex tasks? Well, we just made the connection to humans, so let's think how humans would solve complex tasks. We usually do one of the following, right? Given a complex problem, maybe we can break it into smaller parts to solve individually. We also say, take a step back to reassess the situation, right? That can mean to look at the problem with a new perspective or extrapolate from other cases. If I know how to paint on a sheet of paper, maybe it's similar to painting on a wall. And of course, we can ask for help from others. Collaboration can solve many problems. And this is how researchers in the field motivate their current innovations in artificial intelligence. Whether that's taking multiple cases and extrapolating, like in multitask learning, or breaking down a problem into pieces to work in parallel with other agents, like in federated learning, and sometimes reinforcement learning. These are some popular areas in machine learning that I've tried to bucket into how humans solve more complex tasks. And please check out these areas of machine learning, or feel free to ask us about them in our Q&A at the end. So that's enough about me. We've collectively understood some basics of how machines learn and some of the human practices motivating current innovations in the field. So let's hear from some experts in the areas and the current innovations and see where they think the field will go. I'm first joined by my good friend, Isak Falk. Welcome, Isak.
Thanks, Kate. I'm very happy to be here. Thanks for inviting us into the world of machine learning and AI and telling us about how these model works.
I brought you here today since you're an expert in how machines learn to learn. Would you mind sharing a bit about it?
Yes, I've actually prepared some slides for that, which is good to have. So I am going to present to everyone listening and looking at this stream, thank you for coming, about what learning to learn is and how we can learn to learn and what this means. So as Kate discussed, previously in machine learning, we have gone from learning for one task, one well-defined thing that we want to predict well on. For one example that often people have experience with is, for example, image recognition. So we have images, and these have certain objects in them that we want to classify. The typical example is that we have images of dogs and cats, and we have both the images and the answers, and we would like to know on a new image, is this a dog or is it a cat? And the thing with these tasks is that it's a pretty easy job to do this. We know what we want to find a rule which takes an image and outputs the right label. The issue now that we come to is that these very narrow tasks can be solved, but how do we integrate them into bigger systems which are more complex? How do we design algorithms and machines which can actually take these very good small pieces and integrate them together into something more complex? So as an example, I will first introduce recommender systems and see how they can solve one task, how we can generalize them to more tasks, and specifically how just having one task might not be enough to solve certain problems, but having access to many of them can alleviate these problems and allow us to do things which weren't allowed, well, not allowed, but it weren't possible to do that in the first place. So a recommender system is actually a pretty common thing today. You have it whenever you go shopping in Amazon, for example, recommending items to you based on your previous item history, streaming. So when you stream something, it checks on what you watch and it'll recommend movies based on what you watched before. Similarly, you have, for example, music services, which recommends playlists based on your tastes. A recommender system takes people or users and ratings of items, and it wants to predict what you would rate on things you haven't seen before so that it can recommend good things for you. So I have designed a little task, a toy problem here, where we are a movie rating, we are a movie streaming service, although we only have access to 3 movies, sadly. I think they're pretty good movies. So we have Finding Nemo, we have Fight Club, and we have Love Actually. And we have friend groups. So the items here are on the columns. So column 1 is Finding Nemo, column 2 is Fight Club, and column 3 is Love Actually. The rows here are users. So in our case, we have friend groups. And we believe that since friends often pick each other due to some reason, they do not just randomly fit together, although sometimes this happens. Generally, I think you can find patterns in how friends like things, what they do, and what their preferences are. So here we have Kate, Isak, and Janith, very good friends. And we have watched a subset of the movies. Here, actually, me and Janith have watched all the movies that we have to offer. And we have rated them with a rating, which is this thing from 0 to 10 in the cells of this table. This is also called a matrix in mathematics, but I will just present this as a table, and you can think of it as an Excel table, for example. Here, Kate has rated Finding Nemo and Fight Club. And we wonder, will she love Love Actually? Yeah, will she like Love Actually? And how we do this is by using a learning machine. So I have used this little cyan machine to represent our learning machine. And what it does, it takes as input this table and recognizes that some of these rows look pretty similar. In our case, we can see that me and Kate, Isak and Kate, have pretty similar tastes when it comes to Finding Nemo and Fight Club, while Janith does not share our tastes at all. He does not like Fight Club, he loves Finding Nemo, and he loves Love Actually. So we can infer the following approximate relations in that Kate is similar to Isak, Kate is not similar to Janith when it comes to preferences, and Isak is not similar to Janith when it comes to preferences. So what should we then guess that Kate will score Love Actually as? A little robot checks how me and Janith have rated other movies and says 3 is a pretty good score. Kate will probably rate this as a 3. The problem in the one task setting is, for example, when we don't have access to enough data. So here we have a small friend group, a duo, Steve and Clara, and they have not actually watched many movies at all. We can see that Steve and Clara, they rate Finding Nemo the same, but only Clara's actually watched Love Actually, and none of them has watched Fight Club. So we can't really infer anything reasonable in this case. However, when we go from the single task setting to many tasks, we can instead share information between the tasks. What this means is that we can, for example, use other friend groups to find information in how to fill in the blanks in a case like Steve and Clara. But we can also use meta information to find, for example, archetypical users. And in this case, I've denoted many different tasks, and you see we have different friend groups. They all have watched the same movies because these are the movies we have to offer here. We have Ash, Mr. Brock, famous from the Pokemon franchise, Anakin, Luke, Padme, and Leia. Some of you will know them from Star Wars. And finally, again, Steve and Clara. Some of these people have filled in almost all of the table, but Steve and Clara has not filled in much at all. We see, though, that quite a few of these groups have similarities between them, but they also have similarities within the group. So Ash, Mist, and Brock rate things extremely, either high or low. But we also see that people tend to prefer Finding Nemo and Love Actually together, while not preferring Fight Club, or the opposite way around. So going from one task to many tasks is, I would say, one of the next steps in machine learning, what will help us to go from this narrow sense of machine learning to a slightly broader sense of machine learning, sharing information. I would also say it's personalization of machine learning. So the question becomes, how do we actually share information between tasks? So it's time to go meta in this case. In our case, sharing information between tasks in a meta sense might mean looking at all of this data in a kind of pooled way. And I've used this little white robot to denote the meta algorithm. So what the meta algorithm or global algorithm here does is it finds global patterns that anyone can approximately fit into. Here you see that there's a missing little piece, which should be a broken heart. But what this algorithm does here is it finds pattern among all the users and sees that people can approximately be binned into people who like feel-good movies. That is, they really like Finding Nemo and Love Actually, but they do not like Fight Club that much. However, the other group of movies are thrillers, please. So they would like thrillers. They don't like Nemo. They don't like Love Actually, but they do like Fight Club. So when we have this example of Steve and Clara, how do we actually solve it in this case? We know that when we only have access to this local information on this table alone, we can't really infer a relationship. We can't know what they will score at Fight Club even. But we can actually solve this, at least in a better way than before, by synthesizing meta information and local information. Since Steve and Clara are good friends, since they decided to be in a friend group, they actually share information. So we see that Steve and Clara likes Finding Nemo equally. So we used the little local robot to go to insert the same score for Love Actually. However, we don't know what to score the Fight Clubs for either of them. But we do know that people fall into one or two categories. And since these people have scored high on both Finding Nemo and Love Actually, they probably won't score that high on Fight Club because they like feel-good movies. Another more mathematical treatment of this problem can be found in, for example, in ordinary least squares. For people who don't know what ordinary least squares is, it's essentially the task of trying to find the best fit linear line through a point of data points, for a group of data points. So here I have a two-dimensional data set. They have an x1 axis and an x2 axis. For example, it could be it could be anything. It could be density in the air, and this could be number of anything. Sorry, I can't come up things on the top of my head, but there are two continuous features. And we are trying to find the best fit lines so that we can extrapolate to new data points. So in this case, we want to minimize what is called the sum of squares. You don't have to worry how this looks mathematically, but essentially we want to make this line as close to all of the points at the same time. In one-dimensional, like this only reduces to actually finding the intercept and the gradient. Sorry, I should have stated, it's actually just, this is the x-axis and this is the y-axis, and you're trying to find draw the best fit lines through this. So we want to find the intercept and the gradient. Here, the gradient is called k, and the intercept is called m. M is where we cross the y-axis, and k is how much we will elevate in one unit step to the right. When we have many data points, ordinal least squares is not that problematic. It's pretty simple. In this case, you see that actually, just by looking at this point cloud, there is a line which goes straight through this. But when we only have a few points, it's not that easy anymore. Surely, yeah, we can fit a line through this. And maybe it makes sense for these few data points. But what if the data set was generating more data points? Here we have blue data points, which are from the same kind of distribution, we call it. But you can think of it, it's a mechanism which generates more and more data. And if we generated more data, you see that we would see that the white line is actually not a very good fit, while the blue line is a much better fit. But how do we avoid getting fooled like this? In meta-learning or learning to learn, we can sometimes leverage the fact that when we have many small tasks, these best fit data points, we have data points, but there are a few of them for each task. How do we leverage the fact that they share information between each other? In this case, you see that actually the gradient is the same for all of these tasks, but the intercept is different. Since tasks are related, we can essentially learn a global gradient while fit just one parameter, the intercept, by using the rest of the data. This allows us to actually get much more accurate lines when we have little data available. So just to summarize, sometimes having one task is just not enough. You can't get anything reasonable from this. So what do? Do we just give up? No, I don't think so. I think that by leveraging the fact that sometimes you have access to many different tasks, which might be small in isolation, but they might share a lot of information between each other. So learning to learn, this hierarchical way of looking at tasks, can solve some of these issues through sharing information, matching examples between tasks, and essentially fixing the lack of data that each task might have. Thank you very much for listening. I'll be back soon for the Q&A.
Fantastic. Thank you so much, Isak. A few questions. I know you kind of hinted about this in your presentation, but what are some key terms that you think learning to learn kind of falls under? Like fields in machine learning.
Fields in machine learning. Well, so I think that learning to learn can basically be applied to most things because it's more of a way of assuming that data is generated. So in the real world, I think this is very true in that you have some mechanism which generates tasks, which means that these tasks are coupled. I mean, if I do many experiments, but change some of the knobs, the relationship might be similar, but change a little bit. But since I might have the same physical laws, right, that governs this relationship, they might be similar. So we might only need a few data points. Or in the sense of, for example, generating playlists, we know that users are pretty similar. So even if I've only rated 3 or 4 songs, I think I can start generating pretty good music for this user just by looking at what other people have liked that are similar to this user in some sense. So, if you want to go into machine learning, I think this can be applied for supervised learning, that is regression, categorization, like when you're trying to classification, there's some unsupervised learning, all of these things which fall under machine learning I think most of them can be kind of put in a hierarchical fashion like this, learn to learn. So.
And you mentioned this meta aspect, right? So meta learning is actually a key field in machine learning as like an advanced topic, right? And I guess you have multiple cases and kind of use all of them in your model because it's similar to multitask learning, right?
Yes, but in a sense, I would say that, meta learning, learning to learn, is just a rebranding. So maybe not what everyone wants to hear, but like a lot of these ideas have been around for a long time. And I think that's what people don't realize is that a lot of the things that we do today is not because we've had all these new great ideas, but it's because we had ideas, but we might not have the data. There's one particular big issue. We did not have enough data to actually test these ideas out. We did not have enough, computational power to actually test our algorithms. So I think it's just recently that we reached a point where there was algorithms, there was enough data, there was enough computational hardware and just computational prowess to actually leverage all this information and share tasks. So.
And yeah, I agree. But let's see if Janith shares the same perspective. Maybe he thinks there's something else that's the key to artificial general intelligence and the future of AI than just rebranding. So thanks, Isak. I'll see you in a bit.
Thanks a lot.
Cool. Our next guest is Janith Petangoda. Hi, Janith.
Hi, Kate. How are you doing?
Welcome to Pint of Science.
Thank you. Hi, I'm very excited to be here.
Now, you specialize in a slightly different area of machine learning than Isak. Care to tell us about it?
Yeah, sure. So I'm most interested in the problem of learning transfer. So I think it does have some similarities to at least a lot of similarities to what Isak was saying. But in particular, I wanted to focus on more about the structure of learning transfer and how we can actually write algorithms that can do transfer in the way that we want it to. So I think actually that's what I'll be talking about as well. So
cool, thanks. Go ahead.
Yeah. All right, thank you. So hi everyone. Thank you for being here. I'm Janith, and I'll be giving a little bit of a tour from the research that I've been doing and from the core ideas, at least for the research I've been doing. And so in particular, I'll be talking about the structure of transfer. What I really mean by that is that now Isak told us about how we can learn to learn and what sort of intuitive ideas that we would want from it. And here I'm going to be talking about how we can write models or describe models in such a way that we can explicitly think about what it means to transfer and how we can get the benefits for it. So in order to do that, I'll first be starting by talking about what I think it means to transfer. Then I'll go through a brief overview of how we can write models such that the things that we would want from transfer are present. I'll then give an example of this in practice, which is transfer learning, which is probably a buzzterm that many of you have heard. It's become quite popular these days, and how that works in practice. Then I'll show how this structure that I spoke about gives rise to some of the benefits I would expect from learning transfer, as well as, and then I'll end with where we can go from there. So to start with, what do I mean by transfer? So Isak mentioned that in the sort of next step of machine learning, we want to really think about learning from several tasks together. So here we see a few examples of some card poles which are trying to balance at different positions along the x-axis. So each one of these tasks, each one of these problems can be thought of as an individual learning problem. But in order to, when we think about transfer, we really want to learn something about them together in such a way that the aspects that can be shared between them are actually constant between the things that we learn from it. And the only differences the differences between the models that we learn are actually what's different here. So in this case, you would expect that since all three are trying to balance, that we would want that the aspects of balancing are shared between them, but the only things that are different are where they want to balance. So for example, if we want to, let's say, balance somewhere here, then we really don't need to relearn the fact how we learn to balance, and we really only specify where we want to balance. And really, and honestly, and this is actually from a real problem that I've done, and we found that it is possible to do that, and that when we do learn in this way, we can do some cool things where, for example, here, the card poles that have been learned from the previous problems seems to be stuck. Let me quickly restart my presentation there. Yes. So we see here that the card pole that we learned from the previously has learned how to avoid these asteroids that are falling by specifying where it wants to balance, and hasn't learned at all how to balance again. So it has been given a movement strategy from the 3 previous problems that we learned initially, and has learned that it can just specify where it needs to balance, and it'll go there and balance without a problem. So keep in mind that, for example, the asteroids that are falling here are actually falling, at least some of them are falling where the previous learning problems had learned to balance. So it actually has to balance in intermediate positions. So how can we write our models in such a way that we can do this thing, where we can learn some structure or some inductive bias that is constant between a set of tasks? So one way that we can do this is by specifying that we only want to change a few parameters in the models that we learn when we go between tasks. So, for example, in Kate's presentation, she mentioned that in machine learning, we can often, or in machine, we can think about models having parameters that we tune during the learning process. So here I've shown three models that have been learned for 3, let's say, related tasks. And we can see that some part of the parameters are the same between these 3 models. And really what we want then is that these parameters, the ones that are in the light blue color, are actually the parameters that tell us the model about the things that are constant between the 3 problems. And the color and these smaller parameters, which are the orange, brown, and green, they specify the things that are different. So really this captures the idea that I mentioned before, where we say that the aspects that are different between the tasks is actually a much smaller and less complex component of the full learning problem. And one other aspect of this is that we can also then, within the same set of models, we can learn another sort of inductive biases. So here, given by a slightly different shade of blue, some inductive bias is different from the previous inductive bias here. So here, each of these lines have a specific inductive bias or structure that is constant within them. And then the only things are different between them, or within each one are the smaller parameters. So another way that we could learn how to transfer here is by learning some initial set of parameters given by this x here, such that all the problems that we expect to see are only a small distance away, here specified by the circle. And so the circle tells us what a small distance is. During the learning process. So as Kate mentioned before, during learning, we kind of change the parameters within the data so that the parameters work well for each of the tasks. And really, so then if you think about the initial parameters, the distance here is the difference between those parameter values. And then the tasks that are out here, which are given in gray, are too far away, and so can be transferred to from this position. So how does this work in some, let's say, model setting? So transfer learning is an example of learning to transfer in such using the aspect of changing only a few parameters. So here, initially, we are given a set of tasks, a set of problems, or a data set that is drawn from a set of problems, where we see that the only difference between each of the problems is that their colors are different. So for these, we then start with some initial parameters, and then we do the regular learning process to get some model that works well for all of these problems. Then given a new problem, which is given by this data set here, which is again similar or related to the others in that the only difference between it and the others is that its color is gray, we choose or manually choose some subset of the parameters here given by the orange color, such that when we start with the original model that we learned from the previous step, and then we only update these parameters. So then we only update these parameters as shown here with the orange color. So this can really show us how some of the benefits that we can get from transfer. So let's go back to a much simpler problem where we have two problems A and B. So if we were to, let's say, think about the problem of learning learning models for these in a sort of naive learning from scratch way, we would initially try to learn problem A, where we would start with some input parameters, and then we use learning algorithm to get some parameters that work well for it. Then, given problem B, we would do the same naively, where we start again with some initial parameters, and then we learn the model, the parameters that work well for that parameters given by the different colors here. Now, if we imagine that these two tasks are similar to each other, then we can imagine that the learning cost, which could be the number of data sets, the number of data points we would need, or the computational power that we would need to learn these problems is similar. But if we were to transfer, we would initially start again with problem A and learn its solution as before. But then given problem B, we would again start with the solution that we had for problem A, then choose some, since instead choosing only a subset, we only have to update that from a subset. We can imagine that to learn problem B, we either only need to have less data, or we can use less computational power. And the key reason here is that we've already, in learning problem A, we've already learned some aspect of problem B, which is the part that is consistent or similar between the two problems. Now, another benefit of transfer, which isn't really talked about, and this is really something that I'm particularly interested in my research, is the idea that when we, for example, take the concept of learning to transfer by changing only a few parameters, that we've really learned a continuum of models, right, which can be reached by changing only the parameters that we've chosen to change, that have some consistent inductive bias between them. So, for example, in this case, this set of models rather, can be thought of as a set of models that can, let's say, identify cats, like different species of cats, where the blue parameters that are consistent between them correspond to the catness of a cat, of an image of a cat, and the parameters are different correspond to the different species of cats, for example. And similarly, we have at the bottom here that these models, let's say, are things that can classify dogs, or can identify dogs, where the teal or the darker blue corresponds to the dogness of an image. And then the different colors again correspond to the different species. And this is something I think is quite interesting, as I'll explain in a bit. So where do we go from here? So what are some things that are missing in transfer learning, or like learning transfer, and where do we go from? So I described the notions of transfer in a very high level here, but unfortunately, this is often as far as it goes in the literature as well. So one thing that we're missing in the sort of learning transfer field is a formal notion of transfer. Formal, and by formal I mean mathematical. And then this is important because if we do have this will really allow us to analyze different algorithms and different models that transfer in different ways, and really ask the questions of when does transfer work and why. We can also then ask questions such as, can we measure how easy it is to transfer from one problem to another, given some mechanism of transfer, as well as the problems themselves and the models that we choose. Furthermore, one interesting aspect I think is that in the previous examples, I mentioned that we handpick which parameters we keep constant and which parameters change. And often during the learning process, like when we're tuning algorithms, we can manually change them to see what works best. Is there a way to automate this? So Isak mentioned meta-learning, and meta-learning is something that could be used for this. But really, I'm interested, I think, to ask the question of whether we can ask what the best way to do this. And of course, to do this, we need to know a way of analyzing and formalizing the learning transfer problem. And then finally, given the continuum of models that I've mentioned before, I think one very cool thing that we could do with this is really build an algebra of models where we can think about learning solutions to problems in such a way that we can, for example, combine arbitrary models together, or we can scale them, or we can move along different versions of the model, as I said, with different versions of classifying cats, etc. So I think it's a very exciting field, and there's a lot to look forward to. But yeah, and that's it from me. Thanks for listening, and I think Kate is coming back now.
Yep. Thanks, Janith.
Hi, Kate. Hi.
That was a lot. It was amazing. There's so many topics that we can dig into first, but it's a perfect segue to our discussion in just a second. Really quick though, before we add Isak back in, I wanted to ask you, in your experience, is developing a transfer learning model difficult? Is it just, training a model and then training it again on another data set, or is it slightly more complicated than that?
So, I think, I think in this way, what we mentioned is possible that we could try doing this, but really the question then becomes is that I think if you do that, we're really doing it quite blindly because we don't really know why would it work, right? Like, can we guess beforehand whether it would work or not? And then can we ask questions like how well would it work? Is it actually better that we did it this way rather than just learning from scratch and things like this? So really, we want to do it a bit more, I suppose, scientifically, or maybe with a bit more like precise knowledge or preciseness, such that we can sort of understand what is going on really well. Because as you probably know, that one of the biggest problems with machine learning models is the interpretability. Like, can we interpret what's going on? Can we really tell whether a robot is gonna learn to do something? Could it suddenly do something really bad and end up in a Terminator situation? But yeah, so often the work that I'm particularly doing is really sorry?
I think we're a bit far from that.
Yeah, but if you're not careful. But yeah, so I think a lot of my work is mostly about how we can really think about and write transfer, like learning trends in such a way that we can ask these questions and we can try to answer them. Yeah.
Cool. Well, thank you very much.
No problem.
Without further ado, let's bring Isak back, and then audience. We're now open to questions. Yes, welcome.
Hi.
Thank you.
Hi, Isak.
Hi, both.
So, first up, we hear from Andrew Titman. Oh, a question for me. Why, thank you. Animals learn through a nuanced system of reward and punishment. For example, food, warmth against hunger, discomfort. Is there an AI analog to this? Yes. In fact, in reinforcement learning, there's something called a reward function. And while I could tell you some stuff about it, actually, Janith and Isak know a lot more about reinforcement learning than I do. But the idea is essentially that you have a function and it gives you some new number, and that's your reward. And so positive reward helps reinforce behavior, and negative reward is kind of like a punishment. You guys care to add on to that?
Yeah, so actually, I think that's actually a pretty good way of explaining it. So the example of the carpool that I mentioned, the solution for that was actually from a reinforcement learning problem. So there, in that particular problem, the agent or the machine, the learning machine, doesn't really know much about whether it's a carpool, what it has to do, etc. All it can see is a reward. That if it does this, if it changes its position in a certain way, it gets either a positive number or a negative number or a high number or low number. And its goal is to basically do the things that are necessary in such a way that it will, over time, maximize the sum of its rewards at each time point. So and I think that's pretty much what reinforcement learning, in a nutshell, is. Obviously, there's a lot more nuance to it, but yeah. Yeah.
A very good question. Thank you. Maybe another? From Phil Bellyoung. I've heard people refer to supervised or unsupervised learning with artificial intelligence, or AI. Are either of these learning processes more dangerous than the other? Isak, you want to take this one?
Yeah, I first want to it kind of depends on what you mean by dangerous, because I think it's good to keep in mind that I'll go into what supervised and unsupervised learning are in just a bit, but everything we do in machine learning comes down to these kind of mathematical models, right? And we might know what they're doing, or sometimes we actually don't, but there's still models defined by mathematical operations. So in supervised learning, we're essentially trying to learn a functional mapping from some input space to some output space. We've touched on image recognition. It's a very famous example. You have images, which can be represented as pixels, and these can be flattened to a vector, and you're trying to find some function f, which can be a deep neural network or linear regression or whatever. Logistic regression is also a famous example that maps onto some output space. So in terms of categories, it could be cat or dogs. In terms of continuous covariates, it could be, I don't know, density of of some concentration of some chemical in the air, meteorological indicators, anything, GDP. So the difference between supervised and unsupervised learning is that in unsupervised learning, you're generally trying to learn patterns or structures in an unlabeled data set. So for example, in terms of images, it might mean learning prototypes. It might mean learning PCA is very, very famous. If you have a data set which is formed by vectors, you're trying to find the directions of largest variance. And the difference, I guess, in terms of dangerousness is that in a supervised learning problem, you kind of know what you're trying to get because you're given the answer. But in a supervised learning problem, you don't have the answer because you're kind of presupposing you know what you're looking for. So I don't know if that answered your question with dangerousness, but that's what I have to say on this issue. Over to
so I think I have maybe a different perspective on this. So yes, as is usually the case.
Good.
But I think that so the answer to this question of like whether supervised learning or unsupervised is a bit tricky, because I think at the end of the day, what matters is where these algorithms are used in. So so for example, like Isak mentioned, that supervised learning is that you learn from a function that so you learn some line or some function that maps from input to output. Now the thing is that so obviously the most useful case of a machine learning problem is that we don't really have access to the generating function, so we try to learn something that can be used as a stand-in for it. Now the problem, and then we want to query it or try it out in data points where we haven't actually seen the answer. So the trouble with supervised learning comes in when if we go too far away from the original data set, we don't really know what the behavior is. Like we can't really predict. I mean, we could, depending on how we write the model. So the problem with supervised learning is that if we go too far away from the initial data set we've seen, is the behavior of the learned model predictable or not? And again, that only matters in the context of where we're using it. So for example, if this is again a robot that is trying to do something really important, if it suddenly sees something it has never seen before, and is in a supervised learning sense, it could go and do something completely unpredictable, and then it could mess things up. And similarly, in an unsupervised learning case, again, so as Isak mentioned, like the unsupervised learning could be used to, for example, identifying whether given your object, given the films that you watch, which type of person are you in terms of film watching. So, right, like, do you belong to this group of people who like Love Actually, for example, right? So again, like in that scenario, making the wrong prediction of which group you belong to isn't that bad, right? So you can make mistakes there because, I mean, if someone gives you Love Actually, even though you don't like it, then, you just skip through it. But if it's something more dangerous, then again, that's where I think the danger lies. It's like actually where the models are going to be used. That means that there's also that aspect of like whether which is easier to predict, but I'm not predict behavior in, but I'm not sure I can comment on that, to be honest.
I think we've answered the question enough. Yeah.
Yeah.
Great. Another question for Andrew Tippman, this time to Janith. When using the learner A and going to the learner B, or to learn B, how do you control for solutions to problem B, degrading the capability to deal with problem A?
That's a
little quick note for those who maybe are looking for key terms or topics in this area. This is also known as catastrophic forgetting, as you go from A to B to C to D and you keep going on and on and on.
Yeah.
And that's also in continual learning. So yeah, sorry, Janith, all yours.
So this is actually a good question, and I'm actually not too sure how you can ensure this. And this is actually one of the things that we want to ask research about. So, I mean, I think what I can say is that like, so as Kate mentioned, this is like, so this idea of like, when you transfer from A to B and you lose a lot of information, that is called catastrophic forgetting. It is also, there's another term which is called negative transfer, where learning from scratch in this case is actually better than learning from task A or transferring from task A. So I think, I mean, in practice, I think what I've seen is I think people try, for example, changing a few parameters first and then seeing if that works well or not, and then slowly making it seem more complex. But I, as far as I'm aware, I'm not sure if there's a really formal or like provable way to actually make sure that this doesn't happen. I think it's a very open question out there.
Yeah, and I 100% agree. I know there's also this idea of replay. So as you move, and this is again more in the continual case, as you move from case to case, A to B to C, right, and you're moving further and further away from A, which is what you originally learned on. One thing you can do is you try and save parts of the data set in A, and then as you're training on B, you actually replay and retrain also on some subset of A. And then you run into all sorts of different considerations, right? Like size of memory, how many can you store? Is there a better way of saving it? If instead of saving the actual data points, which we've kind of hinted at before, instead save the parameters for a data generating distribution. Go to statistics for this. And that's just maybe one of the solutions that of many that you can choose from for this kind of problem. But yeah, it is a huge open research question. And I think, once we find the answer, maybe we'll be able to tell where the future of AI is headed, just to bring us back to our theme. But maybe one or two more questions. Cool. Gordon, thank you for your question. Great talks. Thank you, of course. Can it be a trap to assume that certain tasks are similar? Might the similarity be superficial? This is a fantastic question. And I actually want to hand this off to Janith first, if I may, Isak. And then Isak, if you have anything else you'd like to add, please feel free to join in.
Yeah, so that's actually a good question. So I think that, so in practice, yes, so we could have a problem that if we start with assuming that two tasks are similar or related and we kind of may build that assumption into our models, then we can get the kind of problems that we talked about before, which was like catastrophic forgetting or negative transfer, for example. But that being said, though, I think that the next step in learn to transfer is that given a set of tasks, to figure out actually which ones, in which subset of those actually makes sense to be related, to be thought of as being related or similar, and then to write the model in such a way that these sets are the ones that are, or learn the model in such a way that these are the ones that are, related to each other. Of course, of course, this is actually quite a new thing to do, and I'm not entirely sure how exactly we would do it. But I think this is, where the next step of it is, like the meta of meta learning, or like going to the next level of the hierarchy that Isak mentioned. But yeah, Isak, do you have any thoughts?
Yeah, so my thoughts are that whenever you do modeling with machine learning, either you do it explicitly or implicitly, but you assume certain things about how the world works or how your task is. So basically, it comes down to either domain knowledge, which a lot of people speak about. So if you know a lot of things about your data, for example, images, you might know that they have certain structure, that, colors doesn't just change abruptly. It doesn't look like white noise. You have like large patches which have the same color, and you try to actually get this into your model. If you want to have a model which is more generic, but can still learn, you need to get around this somehow. And most of the cases today, I would say, is using more data. I don't think you can get anything for free. Like, there's no master algorithm which can learn anything. The reason why we can learn things is because our universe works in certain ways. There are certain ways that physical laws work, which generates data in particular senses. So in some sense, what we're doing when we're finding these like very good algorithms which can learn anything, we're kind of inching forward by finding optimal implicit representations of the world. So even though it seems like we are kind of learning whatever, we're not really doing that. We're kind of finding certain implicit representations of the universe. So I think you're spot on. Like, if you use a rule or a similarity metric or some way to say that these tasks are similar and it doesn't hold in practice, it might not even be beneficial. It might not even be neutral. You might have negative transfer, it's called, where it might actually interfere with your learning task, and you might get worse performance than if you just learned it in isolation.
Yeah, and I just want to throw in a key term. I was doing a bit of research in preparation for this talk to see how other people have talked about the future of AI. And one thing that definitely stuck out to me was a talk from DARPA on the 3 stages of artificial intelligence. The first one being you have handcrafted knowledge where you have all these rules, and then the second one being statistical learning where you have these models who have a statistical representation and understanding but are lacking in this context and producing like inhuman results. And then the third is this contextual adaptation. And that's the phrase I kind of wanted to steal for tonight as well, because I think we've been hinting about this, and correct me if I'm wrong, of course, guys, but there's a lack of understanding of context. And that's kind of where the field is at now, trying to understand this context. And once you've understood it in some frame of mind, whether that's from statistics or physics or cybersecurity or whatever your expertise is, right? And then being able to adapt it to something slightly similar, a slightly different problem. And I think that's kind of where we're headed. Do you agree?
Yeah, I think so. I think because I think the word context is actually quite important here, because again, like when I mentioned that, for example, given a set of tasks, in what ways is it beneficial to structure this and say that this subset is related and this other subset is related within each other but not to each other, is that is really the context, right? So that the best way to actually optimally decide this, it depends on the context, and the context here could be wherever the model is going to be used, right? So if you were to go back to this RL setting where the agent is kind of put into a particular environment that has some rules, like Isak mentioned, the universe having rules, what is the best way to contextualize the knowledge and the sort of like things that we're observing in such a way that it will best optimize the way that our existence or our survival or whatever, or like whatever objective that we have. So yeah, so like, and the point is that I think the things that we observe don't inherently come with a optimal or a best way of thinking about it or looking at it or solving it. And that really depends on the context. And the context and therefore can be thought of as whatever inductive bias is that makes sense in trying to solve a set of problems or a set of tasks or existing, basically. But yeah, that actually makes a lot of sense.
Kind of like humans, right? You want a good team of people with diverse perspectives. It's the same kind of, by the way, RL is reinforcement learning for those of you maybe not in the field. Just to, define some of our slang as we talk about it. Should we go on to the next question, maybe? Cool.
Yes.
Aiden Wallace, thank you for your question. As industry turns to black box modeling approaches with more important decisions and with less human checkpoints, how important do you feel it is to focus research into explainability of these models? Isak, do you want to take a stab at that one first, maybe?
Yeah, but I'm kind of scared that I'll say something which is wrong or something, because this is definitely not my field. But I'm kind of the opinion that before we should be looking at explainability, I think it's really important to also think about the kind of data we feed to our models, because it also starts there. So I think when you have to think about fairness and all these things, you should think about it not as machine learning models working in this little tiny part of the societal machine, right? I think you kind of need to think about, what are we designing? What are we doing for people? What are we doing for humans? Where does the models fit in? Because like if we just focus on explainability, I think from a societal perspective, we've already lost. Because if I feed biased data, racist data into a model, and then I go like, yeah, model says A, it's obviously correct, then it doesn't matter if we can explain why it says A. I mean, like if all the data is tainted, we can't really do much about it. But I'm going to say before I hold it up to Janith is that I think, of course, it's important that we have some kind of way of interpreting what these models do and not just focus on predicting power. Because in practice, we don't only want a good predicted power, we want to use it not in a vacuum saying like, yeah, we get 89% accuracy. We want to say like, we get 89% accuracy, it doesn't do these harmful behaviors, and also the accuracy is good because it'll allow people to not go hungry or like not be unemployed or something. So that are my 2 cents on this issue.
Okay, I mean, so I think I generally agree with what Isak said, but I think the way I would think about this question is that, so I think, yes, explainability, I think is very important in the sense of, so I think this is actually something that I learned from someone named Timnit Gabriel. She gave a talk a couple of years ago, I believe, at a machine learning summer school. And she had this really good idea about building data sheets for machine learning models. So if anyone's familiar with electrical engineering, or like any sort of mechanical engineering or something, every component that we use comes with a data sheet that kind of tells what its boundaries of behavior are, like where the behavior has been tested within, let's say, temperature or current or voltage, etc. And the model, so these components have been tested within some limit, and then the manufacturer kind of says that within this bound, this is the expected behavior that we would like to see. And anything outside this bounds do not go there. Basically, it's not tested enough. So I think it'll be quite interesting to see if we can do something like that with machine learning models, where we say that, right, we have a model that has been learned from certain behaviors, from certain data sets, and obviously data sets come with biases and things like that. And can we really, once you learn the model, can we test some behavior to see how the model behaves? And can we do it in a sort of scheduled or a formal way, such that we can build a sort of box around, okay, this is how the model behaves within this box, and we are fine with that. We're okay with that, and we can then go forward. So I think, and this kind of thing is quite important, because if we're going to, allocate the decision-making power of important resources of our lives to these machines, then yes, we should really be careful. This comes back to what I said, is the dangerousness of how dangerous a machine learning model is depends on the context it's being used. If the model is just predicting which movies to recommend to me, I don't really care. But if it's something more important, then yes, I think we really need to be able to put boxes around what they behave.
Yeah, and definitely understanding the other key terms to kind of throw out there, the uncertainty and robustness of the model are also key areas in the field, which I highly recommend you look into. We're out of time, sadly, but thank you so much for all the great questions. Feel free to keep the conversation up on Twitter. You can tweet at us directly, or feel free to tweet at Pint of Science, and don't forget the hashtag Pints21. Thank you, Janith and Isak, for taking the time to have a little chat with me and some of the audience members. And thank you to our audience members for participating and being so active in the discussion. It's definitely made it very interesting to hear some of these perspectives, and sparking disagreement with these guys is always fascinating to see where it goes. And of course, thank you to our two team members backstage. We have Maria, who's producing, and Josh, who's picking out the comments for us and helping us manage the show. So thank you to you two as well. And with that, good night.
Good night. Thanks, everyone.
Bye-bye.